A butterfly flaps its wings in Brazil. Weeks later, a tornado touches down in Texas. This is not a metaphor for randomness. It is a warning about how sensitive the universe can be. In some systems, the smallest change can reshape the future entirely. Welcome to Mattermosaic, piecing together the universe, one discovery at a time. For centuries, science believed that if the laws of nature were known, the future could be predicted. From planetary motion to falling objects, the universe appeared orderly and calculable. Yet during the 20th century, scientists uncovered a hidden truth. Some systems follow precise rules, but remain impossible to predict in the long term. This discovery became known as chaos theory. The foundations of predictability were laid in 1687 in England, when Isaac Newton published Philosophia Naturalis Principia Mathematica. His laws of motion and gravitation allowed astronomers to calculate planetary orbits with remarkable accuracy. For over 200 years, this success shaped scientific thinking. Determinism and predictability were treated as inseparable. That assumption fractured in 1889 in Paris. At the Sorbonne, mathematician Henri Poincaré studied the three-body problem, which describes how three gravitational objects interact. While the equations were exact, Poincaré discovered that tiny differences in starting conditions produced radically different outcomes. The system obeyed physical laws, yet its future could not be reliably forecast. This insight remained largely theoretical until 1961 at the Massachusetts Institute of Technology. Meteorologist Edward Lorenz was running early computer simulations of atmospheric convection. When he restarted a simulation using rounded values, the resulting weather pattern diverged completely from the original. A difference smaller than 1/1000th changed the entire forecast. Lorenz concluded that weather is deterministic but extremely sensitive to initial conditions. In 1972, at a conference in Washington, D.C., he introduced what became known as the butterfly effect. The idea described a real physical property of non-linear systems, not poetic exaggeration. During the 1970s, chaos theory expanded rapidly. At Los Alamos National Laboratory in New Mexico, physicist Mitchell Feigenbaum identified universal numerical patterns governing how systems transition from stability to chaos. These constants appeared across unrelated mathematical and physical systems. In 1980, at IBM's Thomas J. Watson Research Center in New York, Benoit Mandelbrot published The Fractal Geometry of Nature. Mandelbrot demonstrated that chaotic systems often generate fractals, repeating structures found in coastlines, clouds, river networks, blood vessels, and galaxies. Biology soon confirmed chaos as a feature of life. Ecologists studying predator-prey populations in North America and Africa during the 1970s and 1980s observed irregular population cycles driven by feedback, not randomness. Medical researchers discovered that healthy heart rhythms exhibit chaotic variability, while rigid regularity often signals disease. Chemistry provided visual proof. The Belousov-Zhabotinsky reaction, first identified in the Soviet Union in the 1950s and widely replicated in the 1970s, produced spontaneous spirals and waves through internal reaction dynamics alone. Even astronomy was affected. Late 20th century simulations revealed chaotic regions within asteroid belts and planetary resonances, showing that long-term orbital prediction has limits. Chaos theory does not claim the universe lacks laws. It reveals that lawful systems can still resist long-term prediction. Measurement limits and feedback loops place natural boundaries on foresight. This realization reshaped science. Forecasting gave way to probability. Single predictions were replaced by ranges and scenarios. Climate science, neuroscience, economics, and artificial intelligence all rely on principles rooted in chaos theory. Order, it turns out, does not require control. It can emerge naturally from interaction and repetition. What once looked like randomness is now understood as structure unfolding beyond precise calculation. Chaos is not the absence of order. It is how order reveals itself in motion. This is Mattermosaic, piecing together the universe, one discovery at a time. If this story changed how you think about unpredictability, tap like share it with someone who still believes chaos means disorder, and let us know what topic you want us to explore next. Subscribe for more weekly journeys uncovering how the universe organizes itself.